Yes? Isospin. Isospin. Because when you, okay, we are not officially started yet, but so this is a wave function for a many body system, a nucleus in our case, that breaks all possible symmetries that are conserved by the nuclear Hamiltonian. One of these symmetries is isospin, but as soon as you have separate wave, as soon as you have Coulomb, you break isospin, and then as soon as you put a separable form for your wave function as a neutron times a proton wave function, you also break isospin. So I just copied back the formula that I finished with yesterday. This is, as I was just saying, the expansion, very formal expansion of the many body wave function of your nucleus, a wave function phi that would break all possible symmetries of the nuclear Hamiltonian, and we can expand it on the basis of states that do conserve those symmetries. And we have some expansion coefficients that are so far undetermined, but we can use these expansion coefficients to extract information about the system. And I think I finished yesterday by saying that the expansion coefficients that are related to n and z, the number of particles, are going to be used to extract the probability distribution of having certain number of particles in a fission fragment, for example. And then the coefficient related to the spin, the angular momentum, are going to be used to extract the spin distribution of these fission fragments. These are techniques that we have developed in the last 3-4 years and that I will very briefly describe. So I will start by talking about the simplest case, which is the particle number projection. And again, I won't give all the detail. I will just emphasize the main physics results. And before we talk about number of particles in the fission fragments, I will just recap what particle number projection is in general in a nucleus. You have a nucleus, Z and N. Forget about fission fragments. It's a nucleus in its ground state. But you are describing it by a wave function like HFB that does not conserve particle number. How can you recover that right number of particles? If you remember, and if I said it, I think I said it, but if you remember, then when I talked about HFB, I said that, well, yes, it breaks particle number, but you can get the average number of particles by putting a constraint on the HFB solution. But that's still the average number. Here we are looking at making sure, so converting this function, we want to turn it into something that is an eigenstate of the number operator. That's the goal. To do this, formally, again, the only thing we have to do is to find, based on this expansion, we have to find a projector, an operator that will sort of, let me write down first this in the simplest case of just one type of particle. So forget about the other quantum numbers. Let's not distinguish between n and z for now, just number of particles. So I have this coefficient here, and I'm looking, and I will use this as, these are states that are eigenstates of the number particle operator. So what I'm looking at is, now what I want is somehow get something like this. So if I can introduce a projector that by definition is such that the projector on n is equal to this, then you can convince yourself relatively easily that the coefficient of the expansion are simply going to be given by this expression. You apply the projector on this, you remove basically all of them except one, then you bracket with the other, well, with the bra, and you use the fact that those eigenstates are orthogonal, orthonormal even. Oops. So those three properties together, you can find that the coefficient of the expansion is given by this expression here. Why is that good? Because we in fact don't need to know really what the state here is. We know what phi here. If we can find a projector, then we can easily extract these coefficients, and this gives us the probability that the symmetry breaking wave function has exactly n particles. That's what we want. What does this projector looks like? Well, again, without proof, just trust me on this. You should never trust me, by the way. I make mistakes, as you found. This is given by this expression here. Yes. And I think that's it. So, sorry, let me write it better. And this is an integral over some angle, which is called a gauge angle, of this object here. This is an operator because n here is an operator. So the exponential of an operator, it's just you Taylor expand it. So this is, infinite sum of powers of this guy. And then there is the number n here that you really want to project on. Perhaps it will make you think of a rotation operator. If you have a rotation operator, it's the exponential of some angle times the angular momentum operator, if that's familiar perhaps. This is the same kind of concept here. You're rotating your wave function, but not in the space of like the real space, but in the abstract space of particle number. That's what this thing actually expresses. So now what we have to calculate is this expression, and so this will, well, this is very simple. Very simple. I'm just writing the full expression, but we have to calculate this kind of matrix element. If I can calculate this, I can calculate the essentially the coefficient that I'm looking for. So in the notes that Enrico is very busy right now uploading, in the version n+1 of my notes, I don't know how many versions there were already, but there are some elements again of how you calculate this. This is technical. I don't want to really enter the details. The one thing though I have to show and open the Pandora's box of second quantization is right now this number operator, it may feel like, what am I talking about? This is very abstract. So in the formalism of second quantization, you can write it like this. This is an integral, and I, again, omit the spin degrees of freedom for simplicity. In principle, the number of operators is applied on fermions, so we have spins that we should take into account, but I want to make the notations a little lighter. So it's an integral of a space of operators. These are field operators. What this operator does, it creates a particle at point R. That's the simplest way to think about it. If you think of the second quantization is designed to facilitate calculations for many-body systems. So typically you work in something called the Fock space, where you have wave functions corresponding, or many-body states corresponding to 0, 1, 2, 3 A particles. You also have a many-body state. So you have one of these many-body states corresponding to 0 particles, which is called a vacuum. And if you act on the vacuum with this operator, you create one particle at point R. If you act with this operator, you are destroying a particle at point R. And when you do this, when you define such an operator, you can prove that this operator, in fact, counts the number of particles in space. And this is the form that we have to plug it in here to calculate this matrix element. Now, in practice, those symmetry breaking wave functions, this, for example, HFB states, you can also express it as function of those creation and annihilation operators, as they are called. And so there are rules to work with them, and this is how we're going to use how in practice we're going to do these calculations. Some of the details are given the references in my notes. This is also given many textbooks on nuclear physics and quantum mechanics, I guess, advanced quantum mechanics, not the basic one, but more quantum many-body methods. But again, for simplicity, I'm skipping this. I have to show this expression, however, because this is how we're going to generalize this to fission fragments. So right now, this is particle number projection for a nucleus. Any question on this? Okay. Now, as I said, what this does is if you have in space, so let's say this is the z-axis, and then you have this. Actually, I think it's gonna be like this. Let's say you have a nucleus in space, a symmetry breaking state corresponding to this deformed shape, and this object would be described by an HFB wave function, deformed HFB wave function. Oh yes, sorry. Yes. Yes. All right, let me try to do this real quick, and so that will be a test to see whether I got it wrong one more time or whether I'm right this time. So we start with this. Right, and then I apply the projector on N, or let's call it N0 to make sure we don't confuse us. So N, and then this is a coefficient, so I have something like this. Now this is gonna be, right? And then I do this. So this means that the summation, all the terms are gonna be dropped except this one. Yes? Oh, sorry. Yes. You mean I should have put this. Yes. This? Yes. The wave function, you mean this one? Implicit, okay, so the expression for this wave function, in fact, if I wanted to be really rigorous, I would say this is a state vector. This is a vector in a Hilbert space, and the many-body wave function as this guy, right? This would be given by this. So this is the bracket formalism of Dirac. So this is the many-body state in the abstract space of the many-body Hilbert space. This is a state vector. And then when you project it on the coordinate representation, this is a many-body wave function. So you have to project on all the coordinates. Then by definition, this gives you this function of A variables. But in this expression, I'm only looking at, I can actually, if I want, I could insert this relation, the closure relation, which are written like this. So-called the resolution of the identity. So the identity operator is given by this. And then if I insert this here and there, I could make the coordinates of the particles appear explicitly. That's one way of making them apparent. More questions? Yes? Which line? This one? This one? Oh, yeah. Yes. Yes. That probably, yes, that's, you're right. That explained the confusion, indeed. Yes. One more. So, this operator here is associated with the number of particles in the entire space in the system that you're interested in. So if I have a nucleus like this, it corresponds to how many particles are in there, knowing that there is nothing outside. But this is not what I want for fission fragments. Now what I would like is, can I generalize this? And now I'm going to make not an attempt at a 3D picture, but a 2D picture. So suppose I have a fission fragment that is something like this. So I have a shape that is close to fission. It's about to break apart and make my two fragments. This is going to be the z-axis of my reference frame, and then this is whatever else axis. And what I want, I don't want to count the number of particles in the whole space here. I just want to count what is in this region, for example. How could I do this? Let's say that this point is as the coordinate, the number, it's going to be a specific coordinate of the neck between the two fragments. How can I sort of use this projection technique to count how many particles there are in this hashed region? And the trick is actually very simple, is to say my number operator in the fission fragment, so let's say in the right, this is going to be the right fission fragment. This is, I'm going to generalize this by saying this is now this object. This is the Heaviside function, or distribution technically, which is 0 everywhere until it gets to the n, and then it's equal to 1. And what that thing does, it filters out everything that is left of Zn. And if I just get the exact same formalism, the projection, number particle projection formalism, but instead of using it with the traditional number particle operator, if instead I use that operator, I can in principle define my coefficient of, I will now write the wave function. So this is going to be, I will actually, what I will calculate is this coefficient here, but let's see. If I apply the projector that is up there, but replacing n operator by this guy, and I calculate this object, then this will give me the probability that I have nr equal whatever number I want in my, so this is the projector. Let's try to not mess up completely the notations. Perhaps I should say, okay, let me try to clean this up a little bit. I'm going to define the projection on the right fragment on particle number n0, and I'm going to write it like this. And then what I'm getting here is this. So this is the projection operator I'm using. I'm projecting on n0 particles, and when I calculate this quantity, I'm getting the probability that the entire wave function of the whole system is such that there are only n0 particle in that subspace here, in the space right of the neck. And of course, if I know there is n0 here, I can also project on the left. And now it gives me that in that, so if I go back to my fission kind of plots, so I go back to collective coordinates where I have, let's say, two collective variables. I have a fission line somewhere. I'm taking a point at fission, and now I'm looking at this single fission configuration. And in that single configuration, I have such a shape, like this. And this particular point has the wave function, which I call phi. And if I calculate this, I will find that in that wave function, if I repeat the exercise for different value of n0, I will find that in that single shape, in that single fission configuration, I have in fact different let's say components corresponding to different number of particles, and I can extract the probability of having each such component. So I can have a distribution of probability, which is norm to 1, so that that is given by those coefficients here. And now I will use, for example, the Langevin method, or another one that I will show in a minute, to say, okay, I want to populate this particular fission configuration has a certain probability of being occupied. And if I occupy this with a certain probability, then I also have to, so I have two distribution of probability. The one that gives me the occupation of any point in that fission line, and then the other one that tells me at each fission point, there is a probability distribution of particle number, and I have to fold those two distributions to get the full yield, the full fission fragment distribution. Even as I was talking, I was thinking it's not very clear. Is it? Should I repeat? Okay. So now that I'm going to try to improvise something, there is danger. So the yield of a given number of protons and neutrons, or given number of proton and total number of particle, this is going to be related to the probability of occupying a certain, let's see, I think I have some notes that perhaps. So this is going to be related to the probability that there is a certain number of particles in my fission fragment, given that there is a certain number of particles in the total nucleus, but this is also at fission for a given fission configuration, and I will call it like this. And then this is going to be folded by the probability of occupying the fission configuration Q. So I will parameterize the fission line by this abscissa psi. And now the probability that I have a certain number of particles is the probability that I occupy that fission configuration, that in that fission configuration there is the right number of particles. So this is the probability of occupying the fission configuration, and that's the probability that in that particular fission configuration I have the right number of particles. Yes or no? Ish. The Langevin equation I was talking about, this gives you this. The projection technique that I'm discussing now, this gives you that. You need to fold the two to get the full yields. If you don't do this particle number projection, you can replace this by saying, well, on average, in my fission configuration psi, I have a certain average number of protons and neutrons. And instead of having a full distribution, I just say it's one value, it's the average value. This is in fact what was done here. And it works. But if you do the particle number projection, you get additional sort of predictive power, additional resolution, because now you're including the fact that every fission configuration contains contributions from different particle numbers. There should be a... Yes? Yes? Congratulations, you're absolutely right. Yes, I skipped that third one because I wanted to simplify, but you're absolutely right that if I do this, I start with the wave function phi in this, yes, here. That is itself doesn't have, this is the wave function for the whole nucleus. That does not conserve particle number. So I'm picking out a specific number of particles in the right fragment, but I am not taking into account the fact that the entire system has an ill-defined number of particles. So what you said is absolutely right. I should do double projection, which in practice is what we do. And the results I will show in the next slide, we did a double projection, so we project on the total number of particles, what I call Z compound nucleus. And we also have to do a projection on Z of the compound nucleus, on N of the compound nucleus, then on Z of the fragment, N of the fragment, so it's technically a quadruple projection. And then we have to fold that with the probability of occupying specific fission configurations. Okay? Yeah, okay. If you do double projection on the compound nucleus and on the right fragment, that automatically determines the left one. You can actually you can do either way. Either you project on the right fragment and the left fragment, or you project, say, on the right fragment and the total nucleus, or you project on the left fragment and the total nucleus, but those three representations are equivalent. So the same kind of concept, if there is no more question on particle number projection, I'm going to talk about yet another type of projection, but I'm going to go much faster, and it's going to be, it should be easier. It's so this projection technique is to get a better estimate of the number of particles in the fragments. But this concept of projection can also be used to extract information on the spin distribution of the fragment. If you remember what we discussed, when the fragments are formed, they are highly excited and they have a spin distribution which can potentially be broad. How can I calculate that? I have yesterday I was explaining that depending on that spin distribution, the number of photons and neutrons that are going to be emitted is going to be very sensitive to that. So is there a way for theorists to predict what that spin distribution should be? And the answer is yes, we can use the same kind of machinery, but this time for angular momentum. So the way it's, and because the angular momentum projection is a little bit more painful, I will really sketch just the results. So this would be angular momentum projection. So here what we are writing, again, as a simplification, is we want something like that. In fact, okay, it should be Jm. So again, we expand our symmetry breaking wave function because our nucleus is deformed, angular momentum is not conserved. So this breaks the conservation of angular momentum. Therefore, I cannot label this wave function with J and M, but I can expand it on such a basis. And now what I want is those coefficients here. And it's going to be exactly the same as before. I'm going to define some projector, and then I'm going to calculate this sandwich here, phi projector now on J and M. And this is going to give me this coefficient square, which I will interpret as the probability that my system has a specific J and M. Again, the technique originally was invented for nuclear structure calculation, and this is literally several decades old. Back in the 50s, they were introducing this angular momentum projection technique. But what is new is to generalize the concept to angular momentum in the fission fragments. And the way it's done is pretty much as in particle number projection. We keep the same formalism, we just change the operator that we are using in the theory. So the full glory expression of this coefficient would be something like this. Where is it? J plus 1/2. Beta. I'm gonna make the simplification that I only have axially deformed nucleus, in which case I'm only projecting on m equals 0. So that's just for simplification. And then I have the Wigner function. Oh, sorry, 0, 0. So I'm taking my symmetry breaking wave function, I'm rotating in space around an axis, y-axis, which is perpendicular to the symmetry axis by an angle beta. That's what this guy is doing. And I'm doing this rotation, and I'm doing a linear combination of these rotations, and that's how I extract the spin distribution, the coefficient of the expansion. Accept without proof. Again, this is old. This is not, I did not invent this, right? So this Ry of beta is gonna be the exponential of beta jy, where this is the angular momentum of the system, the y component of it. So what we do to do the same kind of exercise for fission fragments, we're going to change what this is. Instead of taking the angular momentum, the y component of the angular momentum for the whole nucleus, we're going to define a new operator that is going to be associated with the y component of the angular momentum in the fission fragments. And we need to define it like this. This is the Heaviside function. This particular structure is for symmetry reasons, so that we have the right some right properties. Another way to look at this expression is if you think of the angular momentum, it has an orbital component and a spin component. The orbital component is typically the vector product r times p. R here is to be defined with respect to the center of mass of each fragment. That is a little complication in the formalism. But other than that, again, I don't want to show too much because it gets very gory very quickly. But this is the spirit by which you can use this projection technique to extract the expansion of the spin distribution of the fission fragments. Do you want to ask questions at this point? Oh, this is the small Wigner function. This is you can Google it up. It is related to rotations in space. So this is tabulated. This is easily you can calculate it easily. Yes. Exactly. And because we have a way to calculate the population of these fission points, we can then extract information for all fission fragments. Yes. Very good question. Can we do it? Yes, we are actually doing it as I speak. This is an ongoing project with one of my former postdocs to do exactly that. If you do not, where is it? If you do not take this into account, and you do the double projection here, so you have this, but also angular momentum, then the double projection and angular momentum and particle number just gives you different normalization. But if you now include the probability of populating fission points, there are going to be effects that means that the double projection is not equal to just the product of the two, sort of. This is, I could say it's a very active topic of research because, as I said, it's happening right now. More questions? Okay, so then the last thing I want to say before I show you a couple of slides, including movies, so it's relaxing, and then before we finish, and before it's a break, is the sort of time-dependent generator coordinate method that is going to be used to calculate those yields. Specifically, actually, I should say, those what I call the probability of occupying some fission configuration. So this is an alternative method to extract the population of fission configuration, an alternative method to Langevin, and that method is fully quantum mechanical. I'm going to show just like flash a couple of not flash because I have to write them down, but just write a couple of equations in a particular case for the TDGCM. But this is again the sort of the most advanced method we have right now. So the ansatz now that we take for the wave functions of the system, the many-body wave function, all these many-body methods, it's always the same. You take an ansatz, you make a choice for the formal expression of your many-body state, and then you see what the consequences are. And depending on the complexity of the ansatz, you put in more and more physics. If you start with a Slater determinant, it's a very simple ansatz. If you start putting in pairing correlations in HFB, you're making some more richer, you're taking a richer ansatz for the wave function. GCM is even richer. And it is richer because it's schematically something like this. You generate a family of HFB wave functions, HFB states, corresponding to a vector of collective coordinates. So this is the same thing as before, Q1, Qn, but in practice, n is small. So in principle, this should be an n-dimensional integral, right? This is a very shorthand notation for n-dimensional integral. And then you generate those HFB states, and you make a linear superposition of them with a weight function that now depends on your collective coordinates. That is a kind of basis that you know once you do your HFB once you choose your collective variables and you do your HFB calculations, you know this. What you don't know is these weights. What are the best weights? And as usual, you will determine those weights by saying that the energy computed on this state should be minimal. And that will give you an equation, which is called the Hill-Wheeler equation, that allows you to, in principle, find those weight functions. In the time-dependent version of it, the only thing that changes is that now we add a time here. We allow the system, so now this would be the time-dependent GCM. We will plug in this expression not in the static many-body Schrodinger equation, but in the time-dependent version of the Schrodinger equation, which is something like this. So you're going to plug this in the time-dependent many-body Schrodinger equation, where H is your many-body Hamiltonian, Skirm, Goni, relativistic mean field, blah, blah, blah. And you can, in principle, obtain an equation. The unknown is going to be those weight functions. Still, if you do it, the integral you get, the equation you get, the Hill-Wheeler equation, is particularly hard to solve because it's an integral equation and it's in multidimensional space and whatnot, so it's very difficult. So in practice, people have used an approximation, and the approximation is, let's see. The approximation leads to some nice physics content, which is why I'm showing it. So this is called the Gaussian overlap approximation. Gaussian overlap approximation. And what it's quite painful again to do the derivations. You are basically assuming that your wave function at point Q and the overlap between this and at point Q prime is kind of like a Gaussian with some range, and it's a bit more complicated than that, and there is another approximation that comes with it. But when you do these simplifications, the full Hill-Wheeler equation that you would get becomes the following thing. And lo and behold, you will see how everything sort of is connected. So this would be alpha, beta. So you now have a new object, this function g of q of t. This is a scalar function of those variables and time. And this quantity is the probability of being at point q at time t. So what you obtain is something that looks like a time-dependent Schrodinger equation. There is a time-dependent term. There is a potential term. This is your HFB energy as a function of the collective coordinates q. And then there is a kinetic term, which is not as simple as the p square over 2m, because it includes, again, this collective inertia mass tensor, or collective inertia tensor, which is a function of q. Huh? But if you can solve this equation, you can get the probability that you are at any point on that potential energy surface as a function of time. In particular, you can now calculate the probability that you are at a given fission configuration at time t. And so you're going to use that information to compute the probability P of psi that I was writing down up there. The nice thing with this is that the dynamics of the system in let's say the motion of the nucleus in the deformation space is governed by the same quantities that were used to compute this potential energy surface in the first place. Everything is kind of consistent, and everything can be traced back to the two-body forces that is your personal preference, whether it's Skirm, Goni, or anything like that. So in practice, to get the probability of occupying fission, you would calculate So you can define, based on this probability amplitude, you can define a current of probability. just like in quantum mechanics, and the formulas are in the notes. You can define a probability current, and then if you calculate the flux of that current through any surface at scission, this is how you get the probability of occupying that scission configuration. Going extremely fast because I'm trying to finish before the break, but this is... So this is a little, like, really small snapshot of some of the most advanced microscopic method that we are using today to compute actual fission observables, because the yields that you compute with this, you can compare with experiment. The spin distribution that you compute with this method, you can also compare indirectly with experiments by seeing how those spin distribution change the number of protons, neutrons, and photons that are emitted. And then this particle number projection is related also to the yield calculation. So in this expression, the time would represent the time of scission, the time to reach scission. That one is not going to be compared with experimental data. What you're going to use is you're going to calculate. Okay, so I should say you calculate the flux, the integrated flux over time, until it basically the flux doesn't change, and that's going to give you those yield population. So the time is just the tool, you know. Yes. This time here is not the time of fission, or is not the time of it's just for us a way to populate our different configurations, and what we want is the relative probability of occupation, and that's why we need a sort of time evolution. There is another. I wanted to talk about that too. Okay, there is another approach which is time-dependent DFT, or let's say time-dependent HFB in what is used these days, where it is the time-dependent HFB equation that I showed yesterday. As a recap, it was something like this. I can say... where this was the HFB mean field, the HFB matrix. This is the generalized density of the HFB theory. Those two things depend on time, and the time-dependent HFB theory is this. What this can also be applied to simulate fission, and this time it would simulate fission events. You will start your nucleus, you will calculate your HFB solution at t equals 0, corresponding to, let's say, in 1D, you have your potential energy surface. Let's say you start somewhere here, or somewhere there, somewhere on that surface. That's your HFB solution at t equals 0. This defines a density matrix at t equals 0 and a HFB matrix at t equals 0. Once you have those initial conditions, you can solve this time-dependent equation, and what it does, it simulates the real-time evolution of the nucleus. I will show you a movie. When you do that evolution, starting from, let's say, this point, you wait, you find the system is deforming, and at some point it snaps in two. The time it takes to snap is an estimate of the real time to scission, which is still not measurable experimentally, but it's an estimate of how long it takes to really fission. This is the equivalent of doing a single Langevin trajectory. When you do a Langevin trajectory, I said you have the potential energy surface, and then you follow one of these red lines here. That's a single fission event. You end up in a particular scission configuration. Time-dependent HFB is doing the same thing, but microscopically. It will also, well, kind of the same thing, a similar thing in the sense that it simulates a fission event. The time-dependent generator coordinate method simulates all fission events at the same time. This is a sample of a probability distribution. This is the full probability distribution. Different methods to tackle different things. In principle, if just like in Langevin, they obtain those yields by running many different trajectories. So they obtain these yields by running many, many different trajectories and then sort of combining them together. In principle, one could do a similar exercise with time-dependent HFB, running many different trajectories and then collecting the results to obtain the yields, which can also be calculated directly by using the time-dependent generator coordinate method. And before I let you ask any more question, I will show the movies. Well, I hope it will work actually, because I don't know if this is. So this is, first I'm going to show the movie of the time-dependent generator coordinate method. And what I'm going to show in practice, or if it doesn't work, you can download it from the website and run it yourself. I'm going to show the evolution of this quantity as a function of time. So this is the potential energy surface. Q2 here is the quadrupole deformation. Q3 in this axis is the octuple deformation. The ground state is right here. This is the fission isomer. And that red line, which you will see, cross fingers, a bit later, is the scission line. And the surface is an actual HFB calculation. And now let's see if that works. Yes. The color-coded is the wave packet, is this collective probability amplitude as it spreads across the potential energy surface as a function of time. So we solve this equation as a function of time, and then we just plot. And at some point, you see that it crosses the scission line, and we can, when we calculate the flux of that crossing, this is how we will relate that to the fission yields that are measured experimentally. And we could continue, but this is, there you go. And so when you take this time evolution and you extract the yield based on some of these techniques that I was mentioning, and I don't know if they are still on the board, you get things like this. This is for plutonium-240. This calculation also included this particle number projection technique to get a better sort of resolution of the content in particle number at each scission configuration. So that's the kind of state of the art of what we can do now for plutonium-240. It's a little worse for uranium-235, but not by much. That's the time-dependent generator coordinate method. Oops, sorry. Didn't want to show it again. I wanted to move to the next slide. Oh, yes. The next slide is an illustration of angular momentum projection in the fission fragments to extract the spin distribution. So what is plotted on this figure here as a function of the spin is these coefficients, which, okay, here they are called AJ. I used CJ, but that's the same object. And so this is as a function of J, and for 3 different fragments, what is shown here is that the importance of doing calculations at scission. So those 3 different nuclei, they are near T132. So in their ground state, they are all spherical. If they are spherical, this is the deformation, the energy as a function of the deformation. So all those 3 nuclei are spherical in their ground state. If they are spherical in their ground state and you calculate their spin distribution in their ground state, it would be like a Dirac peak, or very close to a Dirac peak. But at scission, those same 3 nuclei are fission fragments now. They have been promoted to fission fragments, and they are not spherical anymore. They are deformed. And this is reflected in their spin distribution. Tin-132 is still pretty much spherical, but the other 2 are clearly not, because their spin distribution is not centered on 0, but it sort of extends to higher values. When you do this kind of calculation, not just for these 3, but for many other fragments, you can calculate then the average spin of those fragments as a function of the mass of the fragments. This is what you get immediately at scission. This is what you get after you have done the statistical decay of the fragment, the prompt decay. So you've emitted neutrons and photons, and so you've lost angular momentum in the process. So the average spin has gone down. You can still plot it as a function of the fragment mass number. And since I did this morning at 6 o'clock, I should have also added the experimental plot, which is pretty. The experimental plot is not in the same nucleus, but it's in this it's a neighboring nucleus, and it's pretty close to what people have measured. So it's a good. There is no parameter that we have fitted to the data here. It's a pure prediction. In that sense, it's nice because this is a way to make systematic calculations, even in systems where we don't have experimental measurements for this spin. We can just roll out the formalism and do calculation. And then the last but not least, this is again a movie of this time-dependent HFB, which, okay, time-dependent density functional theory. In the particular case, this is time-dependent HFB. So as I was mentioning, this is a time evolution of the system. So you put it in some initial state, and then you let it go, let it be, let it do its things, and it starts deforming. If you have very, very good eyes, you will. I think I was noticing that there were some. So this, you should just look at this one. No? This is the density, and there are some oscillations actually between the fragments. And right now, there it splits. A single fission event, but no, just purely macroscopic time evolution. The beauty of this is that, so this is the illustration of some of the trajectories. One, I mean, it's a different paper, but it's the same group. And so these are some of the trajectories that were computed that correspond to these events. The advantage of this time-dependent HFB theory is that once the fragments have been separated, you can calculate their excitation energy. The total energy of the system is conserved. The fragments that are formed at this time step, they are excited. You can calculate their excitation energy very easily. And you can then compare with experimental data on the total kinetic energy of the fragment. And so this is what I show on this figure. This is the average total kinetic energy as a function of fragment mass for plutonium, for this particular fission. The prediction that comes from this time-dependent HFB calculation are in this corner, in this square here, and that's without any parameter whatsoever adjusted to this fission data. You get a pretty good agreement with experiment. You only get this corner, you don't get the whole curve. That's the downside of this method, but this is at least a prediction that does not rely on fitting anything to data. Okay, that's all I wanted to say for this week. We are at the time of the coffee break. Enrico is still thinking mysteriously about what I said. So should we make a break? And then after the break, it's going to be open discussion. I don't have anything planned. I just wanted to make you relax a bit with this. This is how people in science see each other. I don't know if you know this one. If you're an undergrad and how you see yourself, how your undergrad is seen by a PhD student. And so you can see where you fit on that plot. My two favorites, this one is clearly my favorite. Right? I think some of the postdocs can sympathize with that. I also like this one because it's cute. That's it, coffee break.